Okay. Welcome back. Let me begin. So the last part of my talk is about recent work with Professor Young Choi, and it's basically about the Diabot-Goldman volumes of Hitchin-Riemann moduli space, and the main theorem, or our main theorem, is that this volume is actually infinite if we have a higher rank Hitchin-Riemann moduli space. So let me begin with again Teichmüller space. Let's say F is a compact orientable surface, negative Euler characteristic, and it may have a boundary, say zeta 1 to zeta b. And we define the Teichmüller space is either an isotopic classes of hyperbolic matrix on S, and you assume that there are actually many variations for the Teichmüller space if our surface has a boundary, but we adopt this definition. So we assume that the boundaries are all totally geodesics. And if we do this, we can identify this Teichmüller space with the character variety in the following way. So we collect all the representation that is discrete and faithful, and this totally geodesic condition can be translated this way. So we evaluate this representation at the boundary component, supposed to be hyperbolic element that's the diagonal with distinct eigenvalues. Then we choose as we did last time, the irreducible representation, and any representation of this form will be called the Fuchsian. And I'll give you a Hitchin representation in terms of Labourie and McShane. I did this because our surface is not closed in this case. So we say that a representation is Hitchin if there exists a continuous path from our representation to a Fuchsian representation, but we request that for all t and for all boundary components, its value are, oh, sorry, I missed t here. So rho t of Xi are all loxodromic elements, meaning that they are diagonalizable with distinct eigenvalues. So we collect all the Hitchin representation in this sense and take the PGL and our quotient. And that's the Hitchin component for a compact surface, possibly with boundary. So let us fix some sort of ordered set of loxodromic elements, and then we can define a relative Hitchin component in the following way, as we did for the Teichmüller space. So the relative Hitchin component is the Hitchin component, but we restrict our boundary holonomy in the prescribed data. So that's the relative Hitchin component. And there are, I can list some relevant properties of this Hitchin component and relative Hitchin component. First of all, when n is equal to 2, these two notions are identical. And as Hitchin proved, this space is homeomorphic to a Bohr. It's contractible Euclidean space of certain dimension. And the mapping class group acts on this Hitchin component properly. That's the theorem of Labourie. And when you fix the boundary data, then this relative Hitchin component always admits a mapping class group invariant symplectic form. That's done by like Group-Prasad, Fukushima, Jeffrey, and Weinstein. So I put their name initials there. And of course, if you restrict this form on the supposedly like Teichmüller space, then this form is identical to the well-known Bayer-Peterson form. And we defined Hitchin-Riemann moduli space, or relative Hitchin-Riemann moduli space, as the quotient of our relative or Hitchin component by the mapping class group. Because the mapping class group acts on this space properly, this quotient gives you some manifold structure, possibly with some singularities. And of course, because this symplectic form is mapping class invariant, it descends to the moduli space. So this moduli space, at least there are like regular points, set of regular points are symplectic manifolds with the induced symplectic form. And once you have a symplectic form, we can associate a volume form by taking, nth wedge product of it, maybe possibly divided by some n factorial, whatever. And then, so yeah, that's it. That's the volume that I want to talk about this talk. And when you restrict to the n equals 2 case, this is just a classical Riemann moduli space. And for the classical case, I mean, choosing a hyperbolic element is nothing but choosing a boundary length of boundary length. So the relative Teichmüller space can be written in this way. So the length of a boundary curve is precisely the prescribed length here. And then what Mirzakhani proved is that this space has the finite volume with respect to the volume form that I mentioned in the previous slide. More than that, in fact, she proved that this volume is actually a polynomial in these variables. On the contrary, what he proved is that the volume of this higher rank Hitchin-Riemann moduli space is infinite, provided n is equal to 2. That's our main theorem. So let me outline how we prove this theorem. For the time being, for the simplicity, let's assume that our surface is closed. At the end of the talk, I will give you some remark how we extend our proof to the non-closed case. But for the simplicity, let's assume that S is closed for a moment. And we fix for once and for all an orientation simple closed curve that is separating S into 2 pieces. Because S is closed, there always exists such a simple closed curve that separates S into 2 disconnected subsurfaces. So we fix this with the orientation. Then the proof goes as follows. First, consider so-called, it's very well-known Hamiltonian flow that's done by Goldman. And we choose an open set with positive volume in the Hitchin component such that it has some sort of length spectra non-degeneracy. I will make it clear later. But this property actually prohibits us from finding a non-trivial mapping class group that maps this set back to the original one. Provided we just flow this set far enough. And then if you have done this, we choose a sequence of like divergent sequence that such that this set form a disjoint set of disjoint subset in a moduli space that has the equal volume, and then the sum of their volume gives you a lower bound of the volume of the whole Riemann moduli space. And because this is a Hamiltonian flow, all of them has the same volume. That's why the total space has the infinite volume. So that's our proof. So there are actually 2 most important ingredients. One is this Hamiltonian flow, and the other one is this non-degenerate open set. So I'll explain these two ingredients from now on. So the main ingredient, the first ingredient is the Hamiltonian flow, and that's called the Goldman flow. So how do we construct or define Goldman flow? Well, let's say alpha be an oriented essential simple closed curve that separates surface into 2 pieces. And then because alpha is oriented, and because S itself is orientable, then there's a well-defined notion of being left. So say if we have a surface here, we have alpha here, and alpha is oriented, then there's a left side and right hand side of the representation of the surface. So that's the convention. Let's say alpha S1 is the left side of alpha. And let's say alpha plus and minus be the attracting and repelling fixed points in the Gromov boundary. And we just choose one point randomly from the Gromov boundary of pi1 of S1. Of course, this randomly chosen point must be distinct from the repelling and attracting fixed points of our simple cross curve alpha. And we have seen that for a Hitchin component, Hitchin representation, there is a unique limit curve from its Gromov boundary to the flag manifold. This is a uniquely defined map. So given all this data, we can define so-called alpha Z normalized Hitchin representation. The representation is alpha Z normalized if when you evaluate this representation at alpha, it must be not just conjugate, it must be of this form. So this is the first normalization. And second, we choose Z here. And if you evaluate our limit map at this point Z, it must give you some sum of like standard, I mean, the line spanned by this vector. So this vector, the reason why we choose this vector is just random. You can put any kind of vector here, but yeah, this is kind of most convenient setting. So that's why we choose this. So the lemma is that any Hitchin representation has a unique normalized Hitchin representation in its PGR NR conjugate class. So now we can define a Goldman flow or algebraic bending. So because alpha splits S into two subspaces, we can write its fundamental group in terms of amalgamated product. And let's take a traceless diagonal matrix G. And then we define a new representation by the following property. On the left subsurface, we actually do nothing on it. But on the right kind of subsurface, we make a conjugate of the original representation. And this is called the algebraic bending. So we take an element in the Hitchin component, we lift it as a alpha Z normalized Hitchin representation, and we apply this operation and take the conjugate class. That's the algebraic bending. So and the lemma is that, okay, so if rho is alpha G normalized, and so is this new representation. And we made several choices when we defined algebraic bending. First of all, we choose Z point here quite randomly. But at the end, this algebraic bending doesn't depend on the choice of Z. And also, algebraic bending doesn't depend on the choice of alpha in its free homotopy class. So we can choose conjugate elements. They will give you the same kind of result. But this algebraic bending still depends on the orientation of alpha. And then this algebraic bending gives you a well-defined smooth map from the Hitchin component to itself. And Goldman flow is actually a continuation of algebraic bending. So we just put time t here, and there will be the Goldman flow. And why this Goldman flow is so important? Because Goldman himself proved that this Goldman flow is actually a Hamiltonian flow with respect to Atiyah-Goldman simplex form, or the simplex form made by Guru-Prasad, Fukushima, Jeffrey, and Weinstein. So in particular, whatever it is, in particular, this flow is volume preserving. that's the key point. That's the most relevant part to our talk. So we prove, first of all, this algebraic bending or Goldman flow is actually proper in the following sense. As usual, we pick a oriented essential simple closed curve and let n be a compact subset of our Hitchin component. And then there exists constant C depending only on the choice of n, such that if your traceless diagonal matrix is big enough, has a norm bigger than Cn, then it moves our set n far enough so that this intersection is empty. So proof goes as follows. So we first take the lift of our space n to the space of representation by taking the alpha z normalized Hitchin representation. This is uniquely defined, so this is a well-defined lift. And let's define the set K to be a set of all traceless diagonal matrices where this intersection is non-empty. And because this alpha twiddle is commutes with the projection, this K is actually equal to the set of all diagonal matrices that this intersection is not empty. So we actually need to show that this K is compact. So let me consider the following restriction map that comes from the inclusion. Then what we can observe is that if rho is Hitchin, then it's restricted to a subsurface is also Hitchin. Of course, here this Hitchin means in the sense of Laborde and McShane. And from the definition of our algebraic bending, we have following relations. In the plain language, it just means that if you restrict on the left-hand side, left subsurface, they do nothing on it. And on the right subsurface, it acts as a conjugation. That's exactly what these two identities mean. And let's consider the following set on the right that makes this intersection non-empty. And from this relation, we can observe that K is a subset of K2. But K2 itself is compact because, as I mentioned, if rho is Hitchin, then it's restricted. Restrictions are all Hitchins. And we know that the conjugation action is actually proper on the Hitchin component. So that's why K2 is compact. And K is a closed subset of K2. So that's why K itself is compact. So that's the proof. And from now on, we will consider the following very special Goldman flow. So our G will be given in this form. And if G is given in this form, we will call the associated Goldman flow the Berging flow and denote it by just F alpha and T. And if alpha is well understood from the context, we just drop alpha as well. So we just simply write F of T to denote the Berging flow. And the meaningful Berging flow only appears when n is high enough and is like big enough. Where n is equal to 2, we don't have such a matrix. So before we move on to the next ingredient, let's take a little bit of intermission. So we haven't talked about the action of mapping class group on a Hitchin component. So let me just briefly describe what it is. So the mapping class group is nothing but the quotient of self-diffeomorphism, orientation preserving self-diffeomorphism, modulo is isotopic class. And if you are given a mapping class group element, we can pick a representative that's actual diffeomorphism, orientation preserving diffeomorphism in the class. And then of course induces an isomorphism on its fundamental group, but the base point might be shifted. But if you take the conjugation by a path joining the original base point to the shifted base point, we have an isomorphism from that fixes the base point. Of course, there are a lot of choices involved here. We choose a conjugating path. We choose the representative. But all of these ambiguities lie in the group of inner automorphisms. So you take the mapping class group element, we made a choice, and that, but the ambiguity is just they are all in the inner automorphism. So we have a well-defined homomorphism from the mapping class group into the outer automorphism as on the fundamental group. But this is actually an isomorphism. That's the theorem of Nelson and Baer. So we can identify our mapping class group with the outer automorphism group. And moreover, if you are given an automorphism of your fundamental group, it induces a map on a Hitching component as follows. We just pre-compose, we inverse in front of our representation and take the conjugate class. And you can see that inner automorphism actually acts trivially. So we have a well-defined action of the outer automorphism on the Hitching component, and because our outer automorphism is identical with the mapping class group, we have an action of mapping class group in the Hitching component. That's what I mean by action of mapping class group on the Hitching component. And let's concentrate on the Dan twist. That's the very special kind of mapping class group element. So if you compute its action on the Hitching component, you can see that its effect on the Hitching component can be understood as a algebraic bending. So where T of rho is given by the following form. So this is a diagonal matrix of logarithm, negative of logarithm of eigenvalues of rho of alpha. So important thing is that anyway, this Dan twist is also can be understood as a algebraic bending. And I'm not going to prove this, but some cases, this mapping class group action commutes with the Goldman flow. So let's pick any traceless diagonal matrix that is defined this for the Goldman flow, and let's pick a mapping class group element, and suppose that this mapping class group element has a representative that maps our curve alpha to the curve that is isotopic to itself. If, in addition to this, that this representative F preserves the orientation of alpha, then the Goldman flow Fg alpha on the Hitching component actually commutes with the phi action. Yes, that's a theorem. And let's move on to the next ingredients. We have to find a nice open set that has some sort of degeneracy on its length spectra. To define it, to define what I mean by length spectra, I have to define length. And for Hitching component, the length is defined in the following way. So the length of gamma, the simple closed curve gamma, at some Hitching representation is just a logarithm of the biggest eigenvalue modulo the smallest eigenvalue. But actually, this quantity is independent of the choice of our representation. So we can put any rho prime here in the class of Hitching, the class of whatever representation that conjugated to it. And it also doesn't depend on the free homotopic class of gamma. So we can replace gamma with any other simple closed curve that is freely homotopic to the original one. Also, it doesn't depend on the choice of orientation. So we can flip the orientation and they will give you the same value. So this function is actually really kind of measures the length of the simple closed curve. So one of the main proposition of our paper is this one. So we are given a oriented essentially simple closed curve, and then we extend this curve to the parallel pants decomposition. We choose extra simple closed curves that splits our surface into the disjoint union of pairs of pants. And then there exists a constant epsilon and a non-empty open set n prime in the Hitching component, such that we choose for any I, this inequality holds for all t and all s, all representation from our open set n prime, and for all essential simple closed gamma not isotopic to alpha I. So this is this shows that this n prime has very kind of, their length spectrum is kind of non-degenerate. So to prove this proposition, I need to use very strongly the result of Gieson Lee and Tenggren Zhang. And this is a so-called Kolla lemma for Hitching representation. So what does it Kolla lemma tells you? Well, if you have a Hitching representation, and if you have a simple closed curve, gamma and alpha meeting intersecting kind of essentially, then we have the following inequality. So the length of gamma and length of alpha, they satisfy this condition. So we choose some real number, which is the solution of this equation. And then by this Kolla lemma, if your alpha has smaller length, has length smaller than this particular number, then any other simple closed curve that intersect alpha essentially must have the length bigger than that particular number. We will use this observation in our proof. So let me prove our proposition. So this is our previous observation. If alpha and gamma intersect essentially, and if alpha has a smaller length than delta of n, then the length of gamma must be bigger than delta of n. Now we use the Fenchel-Nielsen coordinate to find a particular single Hitching representations such that all of its Pence curves have length smaller than delta of n. And as well as this condition, we assume we can make the length of alpha I and length of alpha j are all distinct. You can do it by using a Fenchel-Nielsen coordinates. And because the length function itself is continuous, you can perturb a little bit, and these properties still hold without any difficulties. And then our first observation tells you that if you pick any two representation from n prime, and you pick any gamma not isotopic to alpha I, then this must be the case, because either gamma is isotopic to another alpha j, then because we make n prime to have this property, so we have a, even though we put a alpha j here, we still have this inequality. If gamma is not isotopic to any of alpha i's, then by this observation, we must have this quantity must be bigger than delta of n. So we still have this inequality. So in the other case, we have this. And because our Berging flow doesn't change the length of alpha I curves. So, and then in the Kolla lemma, this Kolla lemma is very universal, unless, it doesn't depend on the particular representation. So if you have this, then this property is just follows. So that's actually the proof. And the next lemma just comes from the properness of the action. So if you have a open set here, then there is you can shrink this open set a little bit to have these two properties. That basically tells you that the set of all mapping class group element that doesn't move or u not too far, this is just identity. Same thing for the restrictive one. So our nice open set n will be the n prime and apply this lemma. So you just shrink n prime a little bit to have these two properties. That's our open set n. Now I can prove, I have to state one of our main lemma. So let's choose n as before, and let's just denote by pi of n the projection of each component to the moduli space. Then there exists a particular number n depending only on the compact set n with the following property. Property 1 is that the projection restricted to n flown by time t, they are all injective for every t. And for all s and t, whose difference are bigger than the particular number dn, their intersection in the moduli space is empty. So we can find this number that has these two properties. And once you have this lemma, we can actually prove the main theorem. So we just choose a diverging sequence such that the consecutive difference is bigger than that particular number. And then this lemma tells you that this sequence of open sets are all pairwise disjoint, open. Therefore, the volume of the whole moduli space is bounded from below by the sum of the volumes of each open set. Because phi of f of t preserves the volume form, so we have these volumes are all equal to the original one, and we choose that this is positive number. So the right hand side is actually infinite. This is infinite. So the volume of the whole Hitchin moduli space is infinite. So this is really the key lemma. And to prove this, I have to prove some lemma first. Another lemma, very small lemma. Let's say low and low prime is two Hitchin representations. And suppose that for all unoriented essential class curve beta on S, which is not isotopic to alpha, then we have this inequality, not inequality, like discrepancy. They have a different kind of length. And then for every diffeomorphism that maps Hitchin representation low to low prime, f of alpha must be isotopic to alpha itself. The proof is simple. By definition of the action, the length of this quantity is equal to this. This is a definition of action. Remember, action is what? You just precompose this alpha inverse before the representation. So that's this quantity, and then measure the length of here. So this is a definition of the action. The other end, from the assumption, we have this, because alpha moves low to low prime, so we have this. Then, if f of alpha are not isotopic to alpha itself, then because of this condition, the second condition, we should have the different lengths. But we showed that these lengths are the same, so we get a contradiction. So that means that this f of alpha must be isotopic to alpha itself. Of course, it might flip the orientation, but it's. And remember, we choose n so that this second condition is satisfied. So we have the following observation. So for any mapping class group element, if it maps this element to this element, where rho and rho 2 are in the set n, then f must there exists a representative of mapping class group element that maps alpha to alpha itself, but may flip the orientation. That's the observation. And let me move on to the proof of the main theorem. So let me first prove the easier one. This first item is easier. So suppose not. What does that mean? For some t, if pi restricted to f of t of n is not injective, that means there exists some non-trivial mapping class group element, so that it maps certain element here to another element of this form. That's the negation of our conclusion, and we'll drive some contradiction. So by the observation that we made before, we can choose a representative of our mapping class group element so that it maps alpha to alpha itself, but it may flip the orientation. And if we flip the orientation, it must flip the two subsurfaces. That happens, for example, genus 2 case. So genus 2 surface, if alpha is given in this way, and there is a mapping class that flips one component and the other component. That can happen. But we made our set n so that this kind of bad property will never happen. So meaning that if f exchanges S1 and S2, then there must be a simple cross curve on S1 that has the same length to the simple cross curve in S2. But from our choice of n, all the simple cross curve on the S1 must be different from any simple cross curve from S2. So it never happens. So f cannot exchange S1 and S2, and because f is orientation preserving, it must fix the orientation of alpha as well. So that's the kind of argument. And if you have done this, like if you know that f preserves alpha together with its orientation, then we showed that the phi action, the mapping class group action, commutes with the Goldman flow. So we have this inequality. But then, because this Goldman flow is a diffeomorphism, we have this inequality, but that violates our choice of n, because once this happens, this phi must be the identity. But we assume that phi is not the identity. So that's the contradiction. And this proves the first item. And let me prove the second item. It's actually suffices to show that these two intersections is empty, because for general case, we just apply the first argument, that the mapping class group action and the Goldman flow commits, then we will end up with this situation. So we'll prove this. And we also negate the conclusion. Then there exists a divergent sequence because there's no bound Tn here. So we have a divergent sequence, Ti's, and the sequence of mapping class group elements and sequence of elements in N, such that this quantity returns to the original set N. And then we choose the representative of Phi for each I. And we may assume that Fi pointwisely fix alpha I. And of course, by the same argument that we used in the proof of first item, we can assume that each Fi preserves subsurfaces S1 and S2 and the orientation of alpha. So because Fi preserves S1 and S2, we can restrict F on each subsurfaces, and that will give you a mapping class group element on S1 and S2. And because of our choice of N, Fi restricted to S1 must be isotopic to identity, and Fi restricted to S2 also isotopic to identity. That happens only when Fi is the power of the n-twist along alpha. So this is the n-twist, and this is also a continuation of algebraic bending. So we just unzipped this notation, then we have this, we can write it in terms of algebraic bending in this way for some, power of mi. And then remember that G was given in this vector, and T of phi is given in this form. And because we are dealing with Hitchin representations, these components are all distinct. But we have plenty of components that are identical. That means this vector G and T of rho are never parallel for any choice of rho. And because n is compact set, there is a definite bound for the angle between G and T of rho. Let's say phi of n. This number is positive and depends only on the choice of n. Once we have done this, we can find the lower bound of this vector by taking the orthogonal projection. We have this inequality, and this theta n just comes from the previous slide, and this is this. And because Ti is divergent sequence, so as I goes to infinity, the right hand side of this quantity just diverges. So the left hand side, the norm of this matrix also diverges. But that contradicts our properties of algebraic bending. If you don't remember the statement, this was the statement. So we don't have this quantity, this Cn. So that's the kind of contradiction, and show the second item. So that's the kind of proof for our main theorem for closed surface case. And let me wrap up my presentation by mentioning this surfaces with boundary case. So in that case, we need to consider, we have seen we just used the Goldman flow along a separating simple closed curve. But when we have a surface with boundary of negative Euler characteristic, there are some cases where the surface doesn't have any separating essential simple closed curve. For example, if you have a torus with one boundary component, it doesn't have the separating simple closed curve. Therefore, we need to cope with a Berging flow along a non-separating simple closed curve. That's the first thing you have to do. But this part is kind of technical, but you can do it almost verbatim. You just do the same computation, you do the same argument, and you can make it. And so up to this point, we can actually show that the volume of Hitchin-Riemann moduli space is infinite, provided your surface has at least one essential simple closed curve. Either it's separating or non-separating. But there is one surface that doesn't have any essential simple closed curve. That's the parallel pants. I mean, we are talking about closed surface, compact surface. So the sphere with three boundary components. It doesn't have any essential simple closed curve. So it doesn't admit any obvious bending deformation. So our argument just breaks down for this case. But fortunately, in this case, our Hitchin component is actually the same as the moduli space itself, because mapping class group in this case is just trivial. So we can conclude that the volume of the moduli space is infinite by using the result of Sun, Winard, and Jung. Basically, they construct a proper, global Darboux coordinate on the Hitchin component that is kind of proper. So if you compute the volume, it must be infinite. So that's a kind of complete the proof of our main theorem for all surfaces with negative Euler characteristic. Okay, that's the end of my talk. So thank you for the attention. Maybe question. So